Okay, so at the previous lecture we introduced Banach algebras. We discussed some examples of Banach algebras, and we proved that the spectrum of any element of a unital Banach algebra is compact and non-empty. And today our first goal will be to discuss the spectral radius in Banach algebras. So suppose that A is a unital Banach algebra. A non-zero unital Banach algebra. Then we define the spectral radius. The spectral radius of an element little a in our algebra by the following formula. So this is the supremum of the absolute values of all points in the spectrum. Let's recall that the spectrum is non-empty and compact, so this number is finite. And geometrically, this number can be interpreted as the radius of the smallest closed disk centered at 0 and containing the spectrum. So the picture looks like this. If this is, say, the spectrum, this is the spectrum, and for example, this is 0. Then the spectral radius is the radius of this disk. This is our way. Okay, in fact, we already know something about this number. We know from the previous lecture that the following inequality holds. The spectral radius is less than or equal to the norm. This follows from the previous lecture because, as far as I remember, this was Theorem 2. We proved that for any point lambda in the spectrum, the absolute value of lambda is less than or equal to the norm. So when we take a supremum, we conclude that the spectral radius satisfies this inequality. And there are many concrete examples where this inequality is in fact an equality. Let's look at some examples. For example, suppose that A is the algebra little L infinity, the algebra of bounded functions on some set X. Then it's clear, it's almost clear that for each element of our algebra, the spectral radius is exactly the norm. Well, why is it so? Let's recall that the spectrum of A is the closure of its range. So the spectral radius is the supremum of points in the closure of the range. But of course, we can remove the closure. The supremum will be the same. And we see that this number is nothing but the supremum norm of our function. So we have an equality here. And in fact, the same is true for many other function algebras. For example, the same is true for the algebra of continuous bounded functions, CB of X, on a topological space. Another example. Example 2. Suppose now that A is the algebra of bounded linear operators on a finite dimensional Hilbert space. H is a finite dimensional Hilbert space. So algebraically, this is just the algebra of n by n matrices. And let little a be an operator such that its matrix is diagonal with respect to a suitable orthonormal basis. The spectrum of the diagonal matrix is just the set of all these numbers, so lambda 1 to lambda n. So the spectral radius is the maximum of the absolute values of these numbers. And it's easy to see that this is exactly the norm of our operator. So again, in this case, we have an equality between the spectral radius and the norm. On the other hand, there are many situations in which the inequality, this inequality is strict. Example 3. Suppose that now A is the algebra of operators on the two-dimensional space. So this is just the algebra of square 2x2 matrices. And little a is an operator given by the following matrix. Well, then the spectrum of A is 0, because the spectrum of a triangular matrix is the set of all numbers on the diagonal. So the spectrum is 0, and so the spectral radius is also 0. But of course, the norm is strictly positive, because the operator is non-zero. So in this case, our inequality is strict. And in fact, this example can be generalized as follows. Here's a useful algebraic exercise. If A is any unital algebra, and little a is a nilpotent element, then the spectrum is 0. So moreover, if A is a Banach algebra, then we see that the spectral radius of A is 0, but the norm is not 0, unless A is 0, of course. Okay. Now, in the general case, there is a useful formula for the spectral radius, and this is the so-called Gilfond theorem. Again, we suppose that A is a unital Banach algebra. A unital Banach algebra, a non-zero unital Banach algebra. And little a is an element in our algebra. I claim that the spectral radius of A is equal to the following limit. We take the norm of A to the power n, and then take the nth root of this. And we can also replace the limit by the infimum, and the result will be the same. By the way, this result, well, actually this theorem is due to Gilfond. It was proved for arbitrary unital Banach algebras by Gilfond in 1941. And a bit earlier, Berling proved this result, but only for one specific concrete Banach algebra, the so-called Berling algebra, which consists of some weighted power series. But for arbitrary Banach algebras, so this result is due to Gilfond. To prove this result, it suffices to prove two inequalities. It suffices to show that, first of all, the spectral radius is less than or equal to the infimum. And second, that the spectral radius is greater than or equal to the upper limit. This is the upper limit of the sequence. Well, indeed, why is it so? If we prove these inequalities, then, well, let's recall that for an arbitrary sequence of real numbers, we have the following chain of inequalities. The infimum is always less than or equal to the lower limit, and the lower limit is always less than or equal to the upper limit. If we prove these two inequalities, we see that on the one hand, this number is less than or equal to the infimum. On the other hand, it is greater than or equal to the upper limit. And the resulting chain of inequalities will show that actually all these numbers are the same. And in particular, the lower limit is equal to the upper limit. But this happens if and only if the limit exists. Okay, so now let's prove properties 1 and 2. Property 1 is quite easy. Well, indeed, if we take now any number in the any point in the spectrum, or any point lambda in the spectrum, let's recall the polynomial spectral mapping theorem, which implies that lambda to the power n belongs to the spectrum of A to the power n. And so the absolute value of this number is less than or equal to the norm of A to the power n. And now we take the nth root of this, and we conclude that the absolute value of lambda is less than or equal to A to the power n, and then we take the nth root of this norm. And to get this inequality, we just take the supremum over lambda in the spectrum and the infimum over the natural numbers n. So this implies inequality 1. Okay. The proof of the second inequality is more involved and actually is more interesting. So to prove that the spectral radius is greater than or equal to the upper limit of the sequence, we do the following trick. We consider the following disk, let's denote by D, the open disk on the complex plane of radius 1 over ROA. So this is indeed a disk if the spectral radius is positive, and if the spectral radius is 0, then, well, this is infinity, and in this case, D is just the complex plane. If ROA is 0, then G is just the complex plane. Now we take an arbitrary bounded linear functional, let f be a bounded linear functional on our algebra, and we consider the function psi f. This function is defined on our disk. It is a complex valued function given by the following formula. Well, first of all, why is it defined everywhere on D? Well, indeed, to see that it is defined everywhere on D, we take an arbitrary non-zero lambda in this disk. Clearly, it is defined at 0. And if lambda is a non-zero number in the disk, we can write this function in the following way. We take lambda from here outside, so it will be lambda inverse, or better, minus lambda inverse. And here we have f applied to A minus lambda inverse, the identity, and then the inverse of this element. In other words, what is this? This is the resolvent function of A evaluated at lambda inverse. And this element is indeed invertible. This element is indeed invertible because the lambda inverse, so lambda is in the disk. So lambda inverse is not in the disk. And so the absolute value of lambda inverse is bigger than RV. And so this element is invertible. Lambda inverse is not in the spectrum. So this observation implies that psi f is indeed defined everywhere on D. And moreover, since the resultant function is holomorphic, we conclude that f is holomorphic on the punctured disk. So here we assume that lambda is non-zero. So psi f is holomorphic on the punctured disk on D minus 0. And finally, we observe that psi f is continuous at 0. It's continuous at 0. To see this, we just look at our original formula for psi f. So the inversion is a continuous operation in our algebra. This was proved at the previous lecture. So the continuity of the inverse, of taking the inverse, shows that psi f is continuous at 0. Well, now let's look at the combination of these two properties. There is a classical result in complex analysis, the so-called removable singularity theorem, which states that if we have a holomorphic function in a punctured neighborhood of a point, and if this function is bounded, then it is actually holomorphic everywhere in the neighborhood of this point. So this implies actually that psi f is holomorphic everywhere on D. And so it can be decomposed in the following way. We can write the Taylor series. The Taylor series for this function, Cn lambda to the power n. Okay, let's now calculate explicitly the Taylor coefficients. To do this, we consider a smaller disk. So let now lambda satisfy the following inequality. Suppose that lambda is smaller than 1 over the norm of A. Well, in this case, we can calculate psi f explicitly because the norm of lambda A is less than 1. The norm of this element is less than 1. And we proved, at the previous lecture, we proved an explicit formula for this element in this case. This is just the sum of the geometric progression, lambda A to the power n. And after we apply our functional f here, we conclude that psi f of lambda is the sum from 0 to infinity, f of A to the power n, lambda n. Now we compare this and this. So this decomposition holds on the smaller disk. This one holds on the bigger disk. But if we compare them on the smaller disk, let me draw the picture. This is the disk of radius 1 over the norm of A. And this is the disk of radius 1 over R of A. So we compare them in the smaller disk, and we conclude that Cn is exactly f applied to A to the power n for all n. Okay, now let's come back to this Taylor series. So it converges for all lambda in the disk, as denoted by 1. So 1 converges in D. So this implies that, in particular, this implies that the sequence Cn lambda to the power n is bounded. For all lambda in the disk. Okay, so let's now take any lambda in the disk for convenience. Suppose that lambda is non-zero. And let's recall that f was an arbitrary bounded linear functional. So we know that for each bounded linear functional, this sequence, I write it in the following form, is bounded. So the key point is here. The key point here is that this happens for all bounded linear functionals, and so we can apply the Banach-Steinhaus theorem, which implies that actually in this case, the sequence lambda n a to the power n is bounded in A. The Banach-Steinhaus theorem implies that this sequence is bounded in A. So there is a positive constant C such that the following inequality holds. Now we do the following. We divide by lambda to the power n and take the nth root of this. And this gives us the following inequality. Okay, and now we take the upper limit of this. Conclude that the upper limit of this sequence is less than or equal to the upper limit of this sequence. But c to the power 1 over n goes to 1. And we get the following inequality. And let's recall that this holds for each point lambda, for each non-zero point lambda in the disk. Since this holds for each lambda, we can take the infimum of the right-hand side, and the infimum of the right-hand side is clearly just the 1 over the radius of the disk, but 1 over the radius of the disk is the spectral radius of A. And this is exactly our condition 2. And this completes the proof. Okay, let's now look at some corollaries. Corollary 1 is a special case where the spectral radius is 0. So the spectral radius of an element little a is 0, if and only if the spectrum is 0. And this happens if and only if this limit is 0. And if we now write down this condition explicitly, for each positive epsilon there is a number n, blah, 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 we see that this means exactly that the norms, the sequence of norms of the powers of A, has the following asymptotics. So it decays faster than any geometric progression for each positive epsilon. For example, if this sequence is something like 1 over n factorial, then it satisfies this condition. And there is a special name for such elements. Such elements A are called quasi-nilpotent. Well, the name is quite obvious because the element is nilpotent if and only if this sequence is eventually 0. But quasi-nilpotent means that it is, in general, it is not eventually 0, but it is rapidly decreasing in the sense that it decays faster than any geometric progression. And here's a concrete classical example of a quasi-nilpotent element. Example and an exercise at the same time. Let's look at the Volterra operator. The Volterra operator. The Volterra operator appeared in our second exercise sheet. Let's recall that it is given by the following formula. This is an operator on the space, on the big alto space, on the interval AB. And it acts by the following formula. This is the integral from A to X, K of xy, f of y, dy. So the exercise is to show that this operator is quasi-nilpotent. And actually, this exercise has two sub-exercises. So the easy part is to show that this operator is quasi-nilpotent for each bounded measurable function k. For each bounded measurable function k on the square. And the more difficult exercise, 2, is to show that actually this operator is quasi-nilpotent for each square integrable function. Okay. On the square. In fact, there are many other natural examples of quasi-nilpotent elements, but this one is probably the most classical one. Another useful corollary looks like this. Suppose that A is a unit Banach algebra, and suppose that B is a closed subalgebra, which contains the identity of A. Then, for each element little b in the smaller algebra, the spectral radius of this element calculated with respect to B equals the spectral radius of the same element calculated with respect to A. This is not immediate from the definition of the spectral radius, because let's recall that the spectra, the respective two spectra are in general different. More exactly, the spectrum of B calculated with respect to the bigger algebra is contained in the spectrum calculated with respect to B. So the spectra are different in general, but the spectral radius is the same. And this is immediate from this formula. because, well, this formula is given entirely in terms of the norm, so it doesn't depend on the choice of our subalgebra. Okay, so from now on, we leave the general theory of Banach algebras, and we specialize to the algebra of bounded operators on the Banach space. So what we're going to do is to discuss spectra of bounded linear operators, spectra of bounded linear operators. And we will see that the spectrum of bounded linear operator can be naturally divided into several disjoint parts of the spectrum. Okay, so suppose that we have a Banach space X. X is a Banach space over the complex numbers. T is a bounded linear operator. And by the spectrum of T, I always mean the spectrum of T calculated with respect to the algebra B of X of bounded linear operators on our space. Now, before introducing the parts of the spectrum, let's look at some non-invertibility reasons for our operator. The spectrum is given in terms of non-invertibility. So let's try to understand some reasons for non-invertibility. Well, first of all, the first option is that the kernel of T is non-trivial. And in the finite dimensional case, this is the only option. In the finite dimensional case, an operator is invertible if and only if the kernel is trivial. In the general case, however, we have another option. Namely, it can happen that the kernel is trivial. The kernel is trivial, but the image is not all of X. The image is smaller than X. And these two possibilities cover, these two cases cover all possibilities by the inverse mapping theorem. So if the kernel is trivial and the image is T, the image is X, then our operator is bijective. And we know that a bounded linear operator on a Banach space, if it is bounded and bijective, then it is actually a topological isomorphism. So it is an invertible element of this algebra. Okay, and for technical reasons, it's useful to subdivide this property into two subcases. So the first subcase is the situation where the kernel is trivial, the image is not all of X, but the image is dense in X. The image is dense in X. And the second subcase is the situation where the kernel is trivial and the image is not dense in X. Now, by looking at this picture, we can introduce the following parts of the spectrum of our operator. So we give the following definition. We define the point spectrum of T to be the set denoted by sigma p of T, which consists of those complex numbers lambda for which the kernel of T minus lambda is non-zero. In other words, the point spectrum is just the set of all eigenvalues of T. Next, we define, so this corresponds to the non-trivial kernel. The second part of the spectrum is the continuous spectrum. The continuous spectrum of T consists of those points lambda, which is denoted by sigma c of T. It consists of those lambda which are not in the point spectrum. The kernel is trivial. The image is not equal to x, but the image is dense in x. The image is dense in x. This is the continuous spectrum. And finally, we define the residual spectrum. The residual spectrum of T. To be the set sigma r of T, consisting of those complex numbers lambda, which are not in the point spectrum, and such that the image of T minus lambda is not dense in X. Is not dense in X. So we have three parts of the spectrum. In Russian, point spectrum, точечный спектр, continuous, конечно, непрерывный, residual остаточный спектр. So it follows from the definition that these three parts of the spectrum are disjoint, and they cover the spectrum. So we have the following disjoint decomposition. By the way, in some books, authors of some books and papers define the continuous spectrum in a slightly different way. Oh, I see that I have to restart the Zoom conference. Just a moment. Okay, some authors define the continuous spectrum in a slightly different way. For example, if you take the well-known book by Reed and Simon, then their definition of a continuous spectrum is slightly different. And in particular, these, according to their definition, these parts are not disjoint in the general case. So be careful when you read some book or a paper. Always check what the author means by the continuous spectrum. But according to our definition, which is also quite standard, these three parts are disjoint. And by the way, it's clear that if the space is finite dimensional, then the spectrum is equal to the point spectrum, and the continuous spectrum and the residual spectrum are empty. But this happens in the finite dimensional case. Let's look now at some infinite dimensional examples. Proposition 1. Let's consider the diagonal operator. So we denote by x the literal p space, where p is between 1 and infinity, and we assume that p is finite, or the little c0 space. We take an arbitrary bounded sequence alpha in L infinity, and we consider the diagonal operator m alpha on x, which acts by the following simple formula. It just multiplies each sequence x by alpha, component-wise, alpha 2x2, and so on. So this is one of our main examples of linear operators, the diagonal operator. So what can we say about the spectrum and about the parts of the spectrum? Well, I claim that the spectrum of this operator is the closure of the set of all elements in our sequence. This is the spectrum. The point spectrum is just the set of all elements in our sequence. The continuous spectrum is given by the following formula. So this is the spectrum minus the point spectrum. And the residual spectrum is empty. Well, let's try to prove this result. As usual, we denote by En sequence of the following form. So the identity is at the nth position and 0 is elsewhere. Clearly, En is an eigenvector for our operator, so we have the following equality. And this implies that our sequence, all elements of our sequence, are contained in the point spectrum. On the other hand, if you take any complex number which is not in the sequence, if lambda is not in the sequence, we let beta n denote alpha n minus lambda. This implies that if we now look at the operator m alpha minus lambda, this is also the diagonal operator corresponding to beta. But all the numbers beta n are non-zero, because lambda is not in the sequence. Beta n is not 0 for each n. And this implies that the kernel of m beta is 0. So the kernel, clearly the kernel of the diagonal operator, which multiplies by a non-zero by a sequence which doesn't contain 0, is injective. The kernel is trivial. But m beta is m alpha minus lambda, so lambda is not in the point spectrum. Lambda is not in the point spectrum. So we see that, we conclude that the set of all elements in our sequence is exactly the point spectrum of our operator. And the point spectrum is contained in the spectrum. course. But we know that the spectrum is closed. The spectrum is a compact set, so it is a closed subset of the complex plane. And this inclusion implies that the closure of the set of all elements in our sequence, is contained in the spectrum. Okay, now we want to show that actually these two sets are the same. And to show that they are the same, we consider the following map, that's denoted by phi, from little L infinity to B of x, to the algebra of bounded operators on x. So phi takes each bounded sequence alpha to the respective diagonal operator M alpha. And it's clear that phi is a unital algebra homomorphism. Phi is a unital algebra homomorphism. And let's now recall that a unital homomorphism always reduces the spectrum. So we see that the spectrum of M alpha is the spectrum of phi of alpha. But phi reduces the spectrum. So this is contained in the spectrum of alpha when we consider alpha as an element of little L infinity. But we already discussed some time ago that this spectrum is nothing but the closure of the set of all alpha n's. This is the closure of all elements in our sequence. So we have this inclusion, and if we compare this and this, we see that the spectrum is indeed the closure of the set of all elements in our sequence. Okay, and finally we have to show that all points which are in the spectrum but which are not in the point spectrum actually belong to the continuous spectrum. Okay, again we take any lambda which doesn't belong to the point spectrum. Suppose that lambda is not in our sequence alpha n. So beta n, all the numbers beta n are non-zero. And this implies that each vector En is actually in the image of our operator M beta. En is M beta applied to beta n inverse En. So this belongs to the image of M beta. But the linear span of all the vectors En is dense in X. So the linear span of all these elements En is the set of all the space of all finite sequences. And it is dense in LP, if P is finite, and it is dense in C0. So this inclusion implies that the image of M beta is dense in X. And this completes the proof. So this shows that all points in the spectrum which are not, all points in the spectrum which are not in the point spectrum actually belong to the continuous spectrum. And as a result, the residual spectrum is empty. Okay. In fact, this proposition can be generalized as follows. Proposition 2. Suppose that we have a measure space, omega mu, a sigma finite measure space. Sigma finite measure space. And let X be the big L P on omega, where P is between 1 and infinity, but it's still finite. So we take an essentially bounded measurable function f, that is an element of the big L infinity space, and we consider the multiplication operator mf on LP of omega. So this is just the multiplication operator. It takes each function g to the pointwise product of f and g. Well, I claim that the spectrum of this operator equals the set of all essential values of f. The set of all essential values of our function. This is the spectrum. The point spectrum consists precisely of those complex numbers lambda for which the measure of the fiber over lambda of f inverse of lambda is positive. The continuous spectrum of MF is the spectrum minus the point spectrum. And finally, the residual spectrum is empty. So this proposition generalizes proposition 1. Indeed, if omega is just a set of all natural numbers, and mu is the counting measure, then our operator becomes just the multiplication, the diagonal operator on the little p space. The proof of this proposition is a useful exercise for you. It is a bit harder than the proof of proposition 1, but it's still quite straightforward. A hint is to begin with the point spectrum. So the point spectrum is calculated in a more or less straightforward way. And then try to use an argument similar to this one. By the way, I'd like to stress once again that it's essential here that p is finite. If p is equal to infinity, then the proof doesn't work. So it's an initial question, and this is an exercise for you. What happens if p is equal to infinity? I mean, what happens in propositions 1 and 2? Okay. The next property of the spectrum, proposition 2, is quite trivial, but on the other hand, it is very useful. So let's write it down. Suppose that we have two bounded linear operators. So S is an operator on X, and T is a bounded operator on another bound of space Y. And suppose that they are similar, which means that, let's recall that this means that there is an isomorphism U between X and Y such that T is U as U inverse for some topological isomorphism. U between X and Y. So I claim that if they are similar, then they have the same spectrum. The spectrum of S equals the spectrum of T. The same is true for their point spectrum, for their continuous spectrum, and for their residual spectrum. the proof is a very easy exercise. Well, as a nice application of this observation, let's now calculate the spectrum of the bilateral shift. This was proposition 3. So now proposition 4. Proposition 4. So let's consider the bilateral shift TB, this operator X on the little space on the integers. And it acts by the following formula. So actually it is the right shift, but since the sequences are indexed by integers, this operator is usually called the bilateral shift. So I claim that the spectrum of this operator is the unit circle, bold T. So let's recall that bold T is the unit circle on the complex plane centered at 0. The continuous spectrum is also equal to the circle. And the point spectrum and the residual spectrum are empty. To prove this result, let's identify the little to space on the integers with the big to space on the circle as follows. So for each integer n, we let little fn denote the following function on the circle. So fn of z is just z to the power n. And we know that the set of all such functions is an orthonormal basis. In the big L2 space on the circle. This is the classical trigonometric basis. And from a general theory of Hilbert spaces, we see that there is a unique unitary isomorphism. Unique unitary isomorphism, that's denoted by U, from the big L2 space on the circle to the little L2 space over the integers, which takes each function fn to the standard vector en. As usual, en is the following sequence. Actually, U is nothing but the Fourier transform on the circle. Well, so this isomorphism provides, this isomorphism gives us another operator now on the big L2 space. So let S denote the operator U inverse TB U. So this operator acts on the big L2 space on the circle. And instead of calculating the spectrum of the bilateral shift, we just calculate the spectrum of this operator S. But S is actually is a very concrete operator. Let's observe that TB takes each vector En to En plus 1. And this implies that S takes each function Fn to Fn plus 1. But Fn plus 1 is the pointwise product of F1 and Fn. And this is true for each integer n. So this equality implies that actually S is just the multiplication by F1. F is F1 F for each F in the big L2 space. That is, S is just the multiplication operator MF1. So this is true, this equality is true on the orthonormal basis, and by linearity and continuity, it extends to L2, to the whole space. So our operator is the multiplication operator MF1. And now the rest follows from propositions 2 and 3. So we know everything about MF1. This is the multiplication operator. F1 of Z is just Z, so it is the identity map of the circle. The essential values of the identity map on the circle is just a circle. This is very easy. This set is easily seen to be empty. The point spectrum is empty because because the measure of each point on the circle is 0. And the residual spectrum is also empty. So the continuous spectrum is also equal to the circle. So everything follows from proposition 2 applied to F1, and from proposition 3, which states that the spectra and the parts of the spectra of our two operators, TB and S, are the same. Okay, I see it's time to finish. At the beginning of the next lecture, we discuss another trick for calculating the spectrum. And namely, we discuss some tricks based on duality. And we calculate the spectra, as an application, we calculate the spectra of the right shift and of the left shift operators on the little P spaces. And after that, we we give a brief survey of compact metric spaces. So we discuss some material which you probably know about from your calculus course or from your topology course. And then we apply this material to our study of a very important class of operators, namely the so-called compact operators. And that's all for today. Thank you.